The universe, vast and mysterious, continues to expand, revealing countless phenomena that challenge our understanding of existence. Since 1929, scientists have uncovered a profound connection between our cells and the cosmos, learning that the very elements composing our bodies were forged in the fiery cores of ancient stars. By 1957, it became evident that the night sky, while breathtakingly beautiful, is also a testament to the immense power and complexity of the universe. Amidst this cosmic grandeur, humanity often finds itself questioning its purpose and the mysteries of planets, stars, and destinies that exist in the celestial expanse. Despite these wonders, we often remain indifferent to the universe's unfolding drama until extraordinary events demand our attention. Such is the case with Betelgeuse, one of the largest and most enigmatic stars in the sky. Recently, this colossal red supergiant has exhibited signs of alarming instability, drawing the intense scrutiny of scientists and stargazers alike. Betelgeuse, located more than 640 light-years away from Earth, is a star of staggering proportions that dwarfs our Sun in size. Its colossal nature and striking red hue make it a remarkable celestial object, captivating observers for generations. Even at the speed of light, it would take over 640 years to reach Betelgeuse, a journey far beyond the capabilities of current technology. To put this into perspective, traveling at conventional speeds would take over 12 million years, a duration that surpasses the entirety of human history. This staggering scale underscores the immensity of Betelgeuse, which has recently been observed trembling and pulsating intensely, raising questions about its stability. Stars, while appearing calm and steadfast from Earth's vantage point, are anything but tranquil. Betelgeuse, long classified as a pulsating red supergiant, is a dynamic star whose brightness varies in cycles ranging from 10 to over 2,000 days. These variations reflect its rhythmic expansions and contractions, processes that are visible manifestations of its internal evolution. Its brightness can fluctuate dramatically, ranging from magnitude 5 to magnitude 0, creating a stark contrast with other stars. Significant deviations in its luminosity have been recorded, such as in February 2021, when its brightness reached one of its lowest levels in years. These fluctuations are influenced by its surface temperature, which at approximately 3,500 Kelvin is much cooler than the Sun's 5,500 Kelvin. Despite its enormous size, this lower temperature means Betelgeuse emits less energy per unit area, making it appear dimmer than expected. Recently, its instability has sparked significant concern among astronomers. As a red supergiant nearing the end of its life cycle, Betelgeuse is experiencing dramatic changes in its internal and external structure. The star is gradually exhausting its hydrogen fuel, a process with profound implications for its future. As hydrogen fusion slows in its core, the outer layers expand, causing the star to grow even larger. Simultaneously, helium accumulates around the core, triggering a secondary fusion process known as helium envelope burning. In this phase, helium atoms fuse to create heavier elements like carbon and oxygen, releasing bursts of energy that counteract the gravitational forces trying to collapse the star. However, unlike hydrogen fusion, helium burning is less stable, leading to irregular energy releases that destabilize the star's structure. These irregularities result in pulsations that alter Betelgeuse's brightness and generate powerful stellar winds, which expel significant amounts of mass from its outer layers. These stellar winds reshape the star's structure, affecting its evolution and contributing to its dynamic nature. The rhythmic expansion and contraction of its outer layers, akin to a cosmic heartbeat, further highlight the star's instability. To study these phenomena, scientists use advanced tools like photometry and spectroscopy. Photometry measures variations in the star's light over time, offering insights into its pulsations, while spectroscopy analyzes the light at different wavelengths, revealing details about its temperature and motion. Together, these methods create a comprehensive picture of Betelgeuse's behavior, shedding light on the processes driving its changes. Astrophysicists have also used powerful computer simulations to model the star's internal dynamics. These models incorporate equations governing nuclear fusion, convection, and fluid motion to predict how Betelgeuse will evolve. One intriguing process within the star is stellar convection, where energy generated in the core rises toward the surface. This movement creates convection currents that transport energy outward, balancing the star's internal processes with its external luminosity. These currents also cause variation in brightness, manifesting as the pulsations observed from Earth. The interplay between gravity and radiation pressure is one of the most fascinating and critical factors influencing Betelgeuse's behavior, highlighting the delicate equilibrium at the heart of stellar dynamics. Gravity, the force that pulls matter inward, acts as a constant pressure attempting to collapse the star under its immense mass. Opposing this inward pull is the radiation pressure generated by nuclear fusion occurring within the star's core. Fusion reactions release tremendous amounts of energy, producing outward pressure that counters the force of gravity. This continuous push and pull relationship between gravity and radiation pressure defines the structure and behavior of stars, particularly massive ones like Betelgeuse. In the case of Betelgeuse, a red supergiant nearing the end of its life cycle, this balance has become increasingly unstable. As the star depletes its core hydrogen fuel, the nuclear fusion processes that sustain it undergo significant changes. When hydrogen fusion slows in the core, radiation pressure decreases, causing the gravitational pull to momentarily gain the upper hand. This results in the contraction of the star's outer layers. However, the contraction leads to an increase in core temperature and pressure, reigniting fusion processes, particularly involving heavier elements like helium. This resurgence of fusion generates bursts of energy that temporarily counteract gravity, leading to the expansion of the star's outer layers. These periodic expansions and contractions create dramatic fluctuations in Betelgeuse's luminosity, a phenomenon characteristic of variable stars. During the expansion phase, the star's surface cools, reducing its brightness and giving it a dimmer appearance when observed from Earth. In contrast, during the contraction phase, the surface heats up, increasing the star's brightness and making it appear more luminous. These cyclical changes in temperature and luminosity are not only visually striking, but also provide a wealth of information about the internal processes governing Betelgeuse and other massive stars. Betelgeuse's variability is particularly pronounced due to its immense size and advanced stage of evolution. As a red supergiant, it has already exhausted the stable hydrogen-burning phase that defines the lives of smaller, less massive stars. Its core is now dominated by helium, with fusion occurring in surrounding shells of hydrogen and eventually heavier elements. The fusion of helium into heavier elements such as carbon and oxygen releases less energy than hydrogen fusion, making radiation pressure more erratic and less effective at countering gravity. This instability contributes to the pronounced pulsations observed in Betelgeuse as the balance between gravity and radiation pressure becomes increasingly fragile. These cycles of expansion and contraction are also influenced by convection currents within Betelgeuse. Energy generated in the core is transported outward through convection, a process in which hot plasma rises to the surface while cooler material sinks back toward the core. This dynamic movement of energy creates additional variability in the star's brightness and further complicates the already delicate equilibrium between gravity and radiation pressure. Convection currents can create localized hot spots on the star's surface, leading to uneven brightness and making Betelgeuse appear even more unpredictable when observed from Earth. The study of these cycles offers critical insights into the internal mechanics of massive stars. By closely monitoring Betelgeuse's fluctuations in brightness, scientists can infer details about its internal structure, energy production, and the processes driving its evolution. Advanced tools like photometry, which measures changes in the star's light output, and spectroscopy, which analyzes the composition and motion of its outer layers, allow astronomers to construct detailed models of Betelgeuse's behavior. These models not only deepen our understanding of Betelgeuse, but also enhance our knowledge of the life cycles of other massive stars, many of which will eventually meet similar fates. As Betelgeuse continues to approach the end of its life, the interplay between gravity and radiation pressure will remain a defining feature of its behavior. The eventual exhaustion of its nuclear fuel will tip the balance decisively in favor of gravity, leading to the star's catastrophic collapse and a subsequent supernova explosion. This dramatic finale will mark the end of Betelgeuse's life as a red supergiant, scattering newly formed elements into space and contributing to the cosmic cycle of matter and energy that shapes the universe. Until then, the ongoing observation and study of Betelgeuse provide a unique opportunity to witness the final stages of a massive star's evolution, offering invaluable insights into the forces that govern the cosmos. As Betelgeuse approaches the final stages of its life, its pulsations and convective activity grow increasingly intense. The depletion of its nuclear fuel sets the stage for a dramatic supernova explosion, marking the end of its existence as a red supergiant. Conclusion: until then, the star's dynamic behavior continues to captivate astronomers, offering a rare glimpse into the life cycle of a massive star. The ongoing study of Betelgeuse deepens our understanding of stellar evolution and highlights the interconnectedness of cosmic processes shaping the universe. Through the dedicated efforts of scientists and the use of cutting-edge technology, we continue to unravel the mysteries of this remarkable star, reminding us of the awe-inspiring complexity of the cosmos.